we have discussed about how the bending moment diagram and shear force diagram will be there for simply supported and cantilever beams subjected to four types of loads: concentrated load, UDL, UVL, and external couple. Now today, and I discussed about sagging and hogging bending moment also. So we know that the bending moment due to upward forces is taken as positive, that is sagging. Bending moment due to downward forces, whether it is left side or right side of the section, it is taken as hogging, that is negative. Normally in simply supported beams, we come across sagging bending moment, whereas in cantilever beams, we come across sagging, hogging bending moment. Now today we will see how the relationship between bending moment, shear force and load will be there. So relationship between BM, bending moment, SF, shear force and the load, UDL. Normally the load is taken as UDL here. How they are related. So actually we can always prove that the rate of change of shear force with respect to distance is load. dF by dx is equal to minus W. That is, F is the shear force, X is the distance, W is the load, and the rate of change of bending moment with respect to distance X is shear force. So these two are the relations, very important relations, which we can prove. So this is another important question. Derive the relationship between bending moment and shear force, bending moment, shear force, and load intensity in a beam. Like that they will ask. So we have to derive those two relations. Simple derivation within 2-4 lines you will get that. So to understand the derivation, let us consider a beam AB. See, AB is the beam here. Simply supported beam I have taken, subjected to some loading. So that loading is an arbitrary load. Arbitrary load means anything. So normally that load I will take it as W. It can be UDL or UVL, anything. I will consider a small distance dx. CD is the small element. You can call it as element. CD is an element of this beam of length dx. So dx means it is a very small length. That is the meaning. And I will take that separately here. CD is the small length. So when you take this CD, at C you have the bending moment M. So as I already told, this is a simply supported beam which is subjected to sagging bending moment. So I told you that sagging bending moment means it will be like this. At this end it will be like this. On the other end it will be like this, opposite direction. So it's clockwise, anti-clockwise like this. So that it pushes the beam axis downwards. So deflected shape will be like this. Okay, that I explained in the last class. So I have taken a small length dx. CD is the small length dx. W is the intensity of the load over the small length. And I will take F as the shear force at this end, and naturally shear force at the other end will be F plus dF. I will take this dF as the increase or decrease in that shear force, because shear force changes from point to point. You know that the shear force changes from point to point on the beam, just like bending moment. And I take the bending moment at C as M, bending moment at D as M plus dM, just to identify that these two values are different. Instead of taking M1 and M2, I take it as M and M plus dM, shear force as F and F plus dM. So consider an elemental length CD dx of a beam carrying UDL as shown in the figure. Let M and M plus dM be the bending moment at C and D respectively. I take sagging. And F and F plus dF be the shear force at C and D. So F is the shear force at C, F plus dF is the shear force at D. It acts downwards. We know that shear forces will be opposite in nature. Then M is the bending moment here, M plus dM is the bending moment here. Okay. Now, for this element, we will apply the equilibrium equation. So let us apply sigma Fy is equal to 0. What do you mean by sigma Fy is equal to 0? Upward forces should be equal to downward forces. So that is sigma Fy is equal to 0, or you can say algebraic sum of all the vertical forces is equal to 0. So when you are using RHS as 0, LHS should contain both upward as well as downward forces. So sign convention will be upward forces will be positive, downward forces will be negative. When you add them, RHS should be equal to 0. So that's what the equilibrium equation is. Now, if you apply that here, F is acting upwards, so positive. F plus DF is acting downwards, so negative. Then this W into dx, W is the intensity. So when that intensity is multiplied by dx, you will get the total load. The total force is acting downwards, so therefore minus. So minus W dx is equal to 0. So this is the equilibrium equation, out of which one force is positive because it is upwards. Other two forces are negative. So W into dx and F plus dy, they are negative, so minus. So if you simplify this, F and F will get cancelled. You will be getting df by dx is equal to minus W. So this is a very simple relationship between shear force and load. See here, F is the shear force, W is the load. So df by dx is equal to minus because this minus means it is acting downwards. That is why it is giving a minus W. That's okay. So this is the expression for the relationship between shear force and load. Now to get the expression for bending moment and shear force, relationship between bending moment and shear force, what you have to do is you will apply the equilibrium equation sigma mc is equal to 0. That means algebraic sum of the moments of all the forces taken about the point C and equate it to 0. That is sigma mc is equal to 0. When you are using sigma mc is equal to 0 equation, consider clockwise moments as positive, anti-clockwise moments as negative. Okay. So clockwise moment positive. Now let us see what are the forces that are there. M is the moment. So moment is clockwise. I am taking the moment about C here. So M is clockwise. So plus M. You have to take plus M. M plus dm is anti-clockwise. Even though it is sagging, when you are using clockwise and anti-clockwise, this becomes negative. So minus of M plus dm. Then this F plus df is acting at a distance dx from the C, point C. Since you have to take the moment, so force is F plus df multiplied by distance is dx, and it is giving clockwise moment about C. You can see the arrow. So to move to C, you have to move clockwise. So plus. So therefore it is plus F plus df into dx, that is clockwise moment. Then W into dx is the force acting on this beam, on this element, and it acts at a distance dx by 2. So therefore its moment will be W into dx by 2. Once again, that is also clockwise because it is downwards. So to come to C, you have to move in the clockwise fashion. So plus W dx into dx by 2. So this is the moment equation. So please note that when you are using moment equation, you have to take the force multiplied by distance. When you are writing force equation, only forces we have to take. We should not consider the moment value. So that's why we are not taking M here. We are taking only F and W here. Please note that. So when you are applying moment equation, then you have to consider moment as well as the moment of the force. You have to take. This F is not giving any moment about C because this F is acting at C. So it has no perpendicular distance. So the line of action passes through C. Therefore, F does not have any moment. That means F into 0. That is the moment. That is why I have not written that. So M minus of M plus dm plus F plus df into dx plus W into dx by 2 is equal to 0. That is the moment equation. Here, this dx is very small. When dx is very small, dx into dx will be still small. That means dx square. Dx whole square you will get. That will be very, very small. You can neglect that. So you can neglect this term. And whatever remaining term is there, that you can write. So this m and m also will get cancelled. So you will be left with minus dm plus f into dx. Okay. This df into dx also can be neglected. So please see here, product of two smaller quantities are neglected here. So the terms neglected here are df into dx and dx whole square. Okay, when you cancel out all those things, you'll be getting finally f dx is equal to dm or dm by dx is equal to f. So very simple relationship. So df by dx is equal to minus w is the relationship between shear force and load. Dm by dx is equal to f. It is the relationship between bending moment and shear force. So you can combine these two together. So here w is the load intensity, f is the shear force, m is the bending moment. Okay. Now let us combine these two. what happens? So df by dx is equal to minus w, you know. But we know that f is dm by dx. Put for f here as dm by dx, then what it becomes? It becomes if you differentiate this with respect to x, df by dx is equal to d square m by dx square, or d square m by dx square is nothing but minus w. See here. Okay. So this is the final relationship which relates all the three: bending moment, shear force, and load intensity. So very simple derivation. So two equilibrium equations you have to use for the elemental length of the beam. Okay. So one equation is sigma fy is equal to 0. Another equation is sigma mc is equal to 0. So we are equating, we are considering the algebraic sum of forces, all the forces. When you are taking algebraic sum of forces, take upward force positive, downward force negative. When you are taking moment equation, clockwise moment positive, anti-clockwise moment negative. So like that you have to take, neglecting the smaller terms and simplifying, you will get the relationship between bending moment, shear force, and load intensity like this. So this is what a very important concept. Anyway, if you integrate that, you will get the other way. You don't worry about this. So only up to this you can look into. So df by dx is equal to d square m by dx square, and that is nothing but minus w. So that is the relationship between bending moment, shear force, and intensity of load. So it's a very important derivation. So you have to practice. Next, now we will solve some problems on bending moment diagram and shear force diagram. So please, all of you, open your notebook, write down this problem in the notebook, because it may not be clear here. So I will explain. Just write down this problem. Write down this beam. I will explain how to draw the bending moment diagram and shear force diagram for this beam given loads. So here this is A, this is B. So here what happens? This one moment is acting here. Clockwise couple is given here, 30 kilonewton meter at a distance 2 meter from A. Then UDL is there, 15 kilonewton per meter is the UDL. 10 kilonewton is acting here, concentrated load. It is acting at D. So what I have taken here is, this point is A. This I have taken it as C, where the moment is acting. This is B, and this is D. So reactions will develop at A and B. So A and B are the supports here. This is a overhanging beam. Please note that this is an overhanging beam. So because a portion of the beam is extended beyond this B. So BD is the overhang portion. So distances are 2 meter, 3 meter, and 1 meter. Please write down this. All of you write down this sketch. So now the question is, draw the bending moment diagram and shear force diagram. Find the maximum bending moment and its location. So where the maximum bending moment occurs and its location. Also find the points of contraflexure or points of inflection, if any. So point of inflection means, or point of contraflexure means, it's the point or section where bending moment is 0. So please note that the definition of point of contraflexure or point of inflection means, that is the point or the section where the bending moment is 0. So we have to find the location of that point of contraflexure or point of inflection also. So write down the problem sketch. Only 7 students are there. Okay. Let me explain the problem now. So in any problem, the first step is to find the reactions. So you have to find the reactions. So by using the equilibrium equations, you have to find the reactions. Sigma MA is equal to 0. That is the first equation I am going to use. So you should know how to find the reactions. So let us take RA and RB as the reactions. Now sigma MA is equal to 0. I will take clockwise moments positive. Now I have to take the moments of all the forces about the point A and equate it to 0. So first I will take this UDL, 15 into 5. 5 is the length of the UDL. So this 15 kilonewton per meter is acting over a length of 5 meter. So total load is 15 into 5 and it acts at the midpoint. UDL acts at the midpoint. So midpoint means 2.5 meter from point A. That means this UDL is converted to a concentrated load, equivalent concentrated load acting at the midpoint of UDL. Moment due to that will be 15 into 5 into 2.5. See here, I have written that. That is clockwise. Because it is acting downwards, it is giving a clockwise moment about the point A. Next, this 30 kilonewton meter is a moment given. It is clockwise only. Just add 30 here. Don't multiply by the distance because already it is a moment. You should not multiply by distance. Whether 30 kilonewton meter is given here or here or here, wherever it is, its effect remains same. That is the property of that moment or couple. So plus 30, that's all. So whenever a moment is external moment is given, should not multiply that by the distance. So just take that as 30 plus 30 because it is clockwise. Then this RB. So this RB is the reaction acting upwards. So the moment of this RB will be anti-clockwise. See, I have to come like this. About the point A, I am taking the moment. So RB multiplied by 5. So RB into 5. Distance is 5. It is negative because it is anti-clockwise. Then this 10 kilonewton is giving a clockwise moment. See, 10 kilonewton is downwards. Downwards means to come to A, I have to move like this. Okay, so clockwise. So it is positive. So I am taking clockwise moment positive, anti-clockwise moment negative. So plus 10 into 6 is equal to 0. So this is the algebraic sum of the moments. So 3 clockwise moments are there. 1 anti-clockwise moment is there. Now if you simplify this, you will get the value of RB. RB you are getting 55.5 kilonewton. Then RA we have to find out. For that, you can use that another equilibrium equation. Sigma Fy is equal to 0 or sigma Fv. V means vertical force. That's all. Is equal to 0. So apply that equation. Once again, upward forces positive. When you are using this equilibrium equation, upward forces are taken positive, downward forces are taken negative, sum is taken as 0. So now RA is upwards, RB is upwards. So RA plus RB minus 15 into 5. See, because this 15 kilonewton per meter is acting downwards, its value is negative. So minus 15 into 5 is the total load, minus 10, okay, is equal to 0. So this 30 kilonewton meter you should not take because moment you should not consider when you are writing force equation. This is the force equation. So therefore you should not take this moment. So RA plus RB minus 15 into 5. Minus 15 into 5 is the load, concentrated load acting here. Then minus 10. So if you simplify that and by substituting for RB, you will get RA as 29.5. See, 29.5 you are getting. So if you add these two, you should get the total load, total vertical load. So 55.5 plus 29.5 is 85. You can see that it is 85. If you add these two loads, you should get 85. Definitely you will get 85. 15 into 5, 75 plus 10, 85. Okay, this moment you should not take. So these are the reactions. So once you find the reactions, all these you have learned in your engineering mechanics, okay, support reactions. Now, let us write the shear force diagram first. Shear force diagram we will write first, then we will write the bending moment diagram. See, on that day, I gave you a easy method of writing shear force diagram. All of you observe here. So, first draw a horizontal line. Above this line, we have to plot the positive values. Below the line, you have to plot the negative values. Okay. Now start from this point A. At point A, you have a vertical force reaction whose value is 29.5. The reaction is 29.5. So move upwards by 29.5 because it is acting upwards. So 29.5 kilonewton, you move upwards. So this is the shear force at A. Then after that, there is a UDL. There is a UDL from A to B. The value of that UDL, if you convert to concentrated load, it is 15 into 5, 75. Please be careful here. You understand this procedure here. 75 is the total load here from A to B, which is acting downwards. Now, UDL means it is a straight line. A shear force diagram is a straight line. So now what you have to do is, already you have gone up by 29.5. Now here. Now you have to come down by 75. 15 into 5 is 75. Come down by 75 till this B. So because that load is acting from A to B, so I have to come down by 75 till this B. So what you have to do, 29.5 is there here. So how much you have to come down? So already 29.5 is there here. At B, you have to come down by 45.5. Why 45.5? If you add these two, you will get 75. So the vertical distance from here to here, vertical distance from here to here is 75. So you have to come down by 75. That means 29.5 minus 75 is minus 45.5. So you have to come to 45.5. You have to join these 2 points. Somewhere here, that line cuts this horizontal line. There, the shear force is 0. Please note that. At the point E, if I take this as point E, at point E, shear force is 0. Now let us see at what point that shear force is 0 later. We have to find that point also. What is the distance of that point E from the point E? That we will find out later. So how to draw the shear force diagram I am explaining. At A, you have to move upwards 29.5. Then from A to B, there is a downward force of 15 into 5, 75. You have to come down 75 up to B. Then at B, you have upward force. See here, reaction. What is the value? 55.5. Now from here, you have to move upwards 55.5. So already 45.5 is there down. So another 10 you have to move up. So that means from here to here, the vertical distance is 55.5, which is equal to B. Now you are here. Then there is no force from B to D. Please observe here. There is no force from B to D. That means it is constant. Shear force is constant. When there is no force, it is a horizontal line. Shear force is constant. So then at D, you have a downward force of 10 kilonewton. So come down by 10. Now it closes. So see here. So this is how we have to draw the shear force diagram. Very, very easy method. At A, after finding the reactions, at A, there is a upward reaction of 29.5. Move upwards 29.5. Then from A to B, you have a downward force of 75, 15 into 5. Come down by 75 at B. Then you have a reaction at B, RB, 55.5 kilonewton. Move upwards 55.5. Already 45.5 is there here. Plus another 10 you have to move up. Then there is no force from B to D. It is horizontal. Then there is a downward force at D. It is downward 10. So now whatever value is there above this line, that is positive shear force. Below the line, it is negative shear force. So this is A. From A to E, you have positive shear force. From E to B, so you can make a note that this is point B. From E to B, you have negative shear force. From B to D, you have once again positive shear force. So this is how we have to draw the shear force diagram. That has been explained in steps like this, but I hope this is the easy method. Here I have written all the values of shear forces, but whatever I explained now, that is the easy method of drawing the shear force. Okay. Next, that is left to that it is 0. From 0 to 29.5 it changes. Then at C, you have got the value of a shear force this much. You can calculate always. Then at B it is minus 45.5 to 10 it changes. Then at D it is 10 to 0 it changes. Okay, that's what I have written here. Now to find at the point E, you see here at the point E, you have the shear force value 0 here. At this point E, it cuts this shear force diagram, cuts the horizontal line. Here the shear force is 0. So let us find out at what the distance now. Let me take the distance as x1. X1 is the distance of this E from the point E. That means AE. Distance AE is x1. Let us locate that point where that shear force is 0. So at point E, shear force is 0. at a distance x1 from A. That means shear force at E is equal to 0. Now let us write down the expression for the shear force. Expression for the shear force at E. So this is the point E here. So what happens here is, when you see to the left side of the section, so let us transfer this point E here on this beam. Let us say this is point E. See to the left side. Left side, if you see, left side upward forces are positive shear force. Okay. Left side upward is positive, downward is negative. Okay. So if you see to the left side at a distance x1, I am taking this, and let us consider this E here. This distance is x1. If you see to the left side, RA is positive, but this UDL is negative. Now what happens? RA is 55, how much? 29.5. So 29.5 minus 15 into x. 15 into x1 is the shear load acting over that distance. So since you are writing shear force expression, you should not multiply by the distance. It is shear equation. So when the shear force at E, now you are getting it as 29.5 minus 15 into x1. So all these I had explained in the earlier classes. So if you simplify that, that should be equal to 0 here now, because we know that shear force at E is 0. So it is equated to 0. See here, this is the equation. 29.5 is nothing but RA, minus 15 is that UDL, and the x1 is the distance. So intensity multiplied by distance gives the total load, is equal to 0. If you simplify that, you will get x1 as 1.967 meters from A. So that means what you can say here is shear force is 0 at a distance of 1.967 meters from the point A. Okay, that is how we can compute the distance of distance of the point where the shear force is 0. Now let us see how to draw the bending moment diagram. Next we have to draw the BMD now. So SFD is over. So what we have done is, we have drawn the shear force diagram. At some point shear force is 0 at the point E, and we have located the distance of that point from the support A also by equating the shear force at that point to 0. Okay, that's what we have done. Next is bending moment diagram. So to draw the bending moment diagram, what you have to do is, you have to start calculating the bending moment at different points on the beam. So let us see. We know that bending moment at A will be 0, because bending moment at A will be 0 because it is simple support. So that you know. Then bending moment you have to calculate at 2 points at the point C. So why we have to calculate at 2 points? Because a moment is given there. Because the external moment is given at C here. So I have to there will be 2 values of bending moment here. So let's just take left side of C and also right side of C. Let us calculate left side of C. Just to the left of C means MCL. MCL means it is the bending moment just to the left of C. So somewhere here, okay, here. So if you calculate the bending moment, C to the left side of that section, upward forces cause positive bending moment, downward forces cause negative bending moment. Okay, that's what you have to see. Now, if you use that concept, so this RA is upwards, so 22.5 multiplied by 2 meter. So 22.5 into 2 is the bending moment due to this. Then bending moment due to UDL is negative because it is downwards. 15 into 2, that is the load. 15 into 2 is the total load. Into it acts at 1 meter. Midpoint from here to here, because we are measuring the distance from C. So you have to take the midpoint of UDL from A to C. So 15 into 2 into 1. So it becomes 30. So finally, so this moment is not seen here, because I am just seeing just left of C. Left of C I am seeing. So since I am seeing to the left side, the moment is acting at C. Since I am left of C, this moment is not seen there. So the value of bending moment just to the left of C will be 29.5 into 2 minus 50 into 2 into 1. So that value will be here. How much? Just see here. Yeah, kilonewton meter. 29 kilonewton meter is the value of bending moment just to the left of C. Just to the left of C. Now, we have to take one more value just to the right of C. When you are calculating just to the right of C, be careful here, all of you observe here. When you are calculating bending moment just to the right of C, this 30 also we have to consider. This 30 also we have to consider. Because I am now here. I am now here. When I am now here, I am seeing if I see to the left side of that, this 29.5 into 2 will be there, minus 15 into 2 into 1 will be there, and also this 30 also is seen. But how to take this 30, whether it is positive or negative? So what happens? Suppose you are given here 30 kilonewton like this, it is like sagging. It is a sagging moment. So 30 kilonewton meter is a sagging moment. Sagging means it acts like this. Hogging means it is in the anti-clockwise sense. Okay. So therefore, you can have to take this as sagging, or you can think in another way. You can assume a upward force here. If you have an upward force here, it gives a clockwise couple. Okay. Is it not? This, for example, this RA is there. RA is giving a clockwise moment about this C, Like that, since you can always say that this moment can be replaced by an upward force separated by a distance. Therefore, it is positive. So, since it is giving a clockwise effect, so it is positive. So, if you are here, just to the right of C, the value of bending moment will be 29.5 into 2 minus 15 into 2 into 1 plus 30. So just you have to add that value because it is a moment. You should not multiply by the distance. See here. That's what has been done here. And it is written as MCR. MCR means it is the bending moment just to the right of point C. So this is bending moment just to the left of point C. This is bending moment just to the right of point C. You can observe here the difference between these two is 30. This is 29. This is 59. So difference is 30, which is nothing but that external couple given. Next point is we want the bending moment at B. So bending moment at this point, see here. So when you want to calculate bending moment at this point, you need not see to the left side of that, you will see the right side of that. Because whenever you want bending moment, either you can see left side of that or right side of that. Here let us take right side of that because there is only one force is there. So the 10 kilonewton is there. 10 kilonewton is acting downwards. Downward means negative bending moment. So minus 10 into 1. Distance is 1 meter. So minus 10 into 1 is the bending moment at B. So that you can write MB as minus 10, which is minus 10. And what is the bending moment at D? The bending moment at D is 0. The reason is there is no force. If you see to the right of D, there is no force to the right of D. Last point is D, is it not? So if you see to the right of this becomes a free end. You can see that this becomes a free end. So bending moment here will be 0. So that means now you have calculated the bending moment at 5 points. One is at A. At A it is 0 because if you see to the left of A, nothing is there. So it is 0. So MA value is 0. Then we have taken MCL. MCL is 29. MCR is 59. MB is minus 10. And MD is 0. And if you plot the diagram, bending moment diagram, see it will be like this. At A it is 0. See, observe here. At A it is 0. At C you have two values. One is left side, another is right side. First you have to plot the left side value, which is 29. Then you have to take the right side value, which is 59. So 0, then 29, then 59, then minus 10. Minus 10 means you have to plot below this. At B, it is minus 10. I have not written the A, B, C, D here. You can please make a note of that. A, this is A. This is CL value. This is CR value. Then this is B. So somewhere here B will be there. Minus 10. Then at D, it is 0. So it closes. Bending moment diagram closes. You see here. Finally, it becomes 0 here. Now that means, now how we have to join that? That is very important. It is a UDL. See here, from A to B, it is UDL. UDL means bending moment diagram is a parabola. I had explained in the last classes. So if it is concentrated load, bending moment diagram is a straight line. If it is UDL, it is a parabola. If it is UVL or triangular load or trapezoidal load, it is cubic parabola. So you have to join by a smooth curve now, like this. It's not a straight line because from A to B, B is here. From A to B, you have to join the bending moment values by parabola only. So here it is parabola. Then here you have two values, just straight line. So where a external couple is given, bending moment diagram is a vertical line. So it is a vertical line. Two values will be there. Then once again parabola because up to B you have the UDL, parabola, then straight line. See, please write here. This is parabola. This is also parabola, but this is a straight line. Please write down that parabola. This is parabola. This is straight line because UDL is given from A to B. Now, if you observe this bending moment diagram, the values are in kilonewton meter because it is moment in force into distance, So shear force value will be in kilonewtons, bending moment value will be in kilonewton meter, force into distance. Now, if you observe this BMD, one at some point F, I take this point as F, bending moment value is 0 because it cuts the horizontal line. So here it is 0. Above this line it is positive. Below the line bending moment is negative. That means from A to F, the beam is subjected to sagging bending moment, positive bending moment, whereas from F to D, the beam is subjected to hogging bending moment, minus. Okay, this is how we have to analyze the diagram. Now we have to find this distance where this bending moment is 0. Just like where the shear force is 0, that point E we have found out, by equating the shear force is equal to 0 at the point E and solving for x1, we got the value of x1. Here also, I take this distance as x2. x2 is the distance of point F from the point A where the bending moment is 0. So this point is known as point of contraflexion or point of inflection. So sometimes you may have more than one point also. Sometimes depending on the load, the bending moment may be negative, then once again it may come positive. There once again you will be having one more point of contraflexion. Okay, later on we will see. In some problems you may get 2 points of contraflexion also, but in this problem you have only one point of contraflexion or point of inflection, which is called as 0 bending moment point. So how to find this? I will take the distance as x2. Now what I have to do is I have to write the expression for bending moment at F and equate it to 0. That's all. Simple. I have to take the expression for bending moment at F and equate it to 0. So you will get the unknown x2. So let us see how it is done. See here, it has been done. It is done here. So MF is equal to 0. What is MF? Bending moment at F is equal to 0. That is the point of contraflexion. Now let us start writing the expression for MF by taking left side of the section because the distance is measured from the left side. Let us take the expression from the left side. So bending moment at F. So you can transfer this F onto the beam diagram. So it will come somewhere here. Somewhere here it will come. See, this will be F. Just like E. E will be somewhere here. F will be somewhere here. Now what I am doing is, let us take this as F. Consider left side of this. Write down the bending moment expression. So RA into this distance. Distance is x2 I have taken. So 29.5 into x2. Positive. Then UDL is there. UDL is giving downwards. So bending moment is negative. So minus 15 into distance is x2. From over this x2 distance that UDL is acting. Minus 15 into x2 divided by 2. Because it acts at the midpoint. When you are taking the moment, this UDL is converted to concentrated load and it is assumed to act at the midpoint. Okay, so that's why moment will be 50 minus 15 into x2 by 2. Then this 30 kilonewton meter also we have to take it, as I already told, it is positive. So plus 30. So these things we had to, that is the bending moment. So if you take point F here, if you take left side of that point F and if you write the bending moment expression, 29.5 into x2 minus 15 into x2 by 2, then plus 30 is equal to 0. Because we know that that value is 0. See, that's what I have written here. That is the expression I have written here. See here. This is the expression is equal to 0 because it is the point of contraflexion. We have to equate this to 0 and solve this. So you are getting a quadratic equation. So solve using the formula method. You will get two values for x2. One value you are getting minus 0.438. Another value you are getting 4.77. Okay. So among those two, you have to take the positive value. Negative value you have to discard. So x2 value is 4.772 meters from point A. So this is the point of contraflexion. I will tell you another method. You can just try that today. You just try that for the same problem. You can calculate this distance of this point of contraflexion by considering right side also. Right side also. So what you can do is, I'll just give you the hint how to do that. You will get the same answer. So I will take from this point D to this F as x2. Instead of taking from A as x2, I will take from this end as x2. And I will write the expression for the bending moment now. So what I am telling you here is, you know that F is here now. I will take this distance as x2 from the point D. Now, if you want to write the bending moment expression, this 10 kilonewton is acting downward, so bending moment is negative. So whether it is left side or right side, downward force give negative bending moment, upward force give positive bending moment. So 10 kilonewton is giving down negative bending moment, RB is giving RB is giving positive bending moment. And now let us, and this small portion of UDL is also there. So that also will give negative bending moment because it is downward. Okay. So like that also you can do. The minus 10 into x2 will come. Then plus RB value, which is 55.5 into this distance is 1 meter, you know. So it becomes x2 minus 1. X2 minus 1 is this distance. So this RB will be at a distance of x2 minus 1, okay, from this point F. Then this UDL is there, you know. This UDL will be over a length of x2 minus 1 only. X2 minus 1 only. So what you have to do is minus 15 into x2 minus 1 into x2 minus 1 divided by 2. Like that we have to do. Okay. So like that, if you calculate, you will be getting the distance x2. Anyway, whichever is comfortable for you, you can use that. But you will get the same value. X2 will be, in that case, what is the value of x2? Here you got 4.772, you know, from this end A. So probably you may get 1 point something if you take from this end. Okay. So the position of that F won't change. So anyway, whichever is convenient, whether left side or right side, you calculate the bending moment expression and equate it to 0. Of course, here you are getting, by considering left side of the section, you are getting this as the value. Now the next question is, where the maximum bending moment occurs. So if you observe the bending moment diagram here, where the maximum bending moment is, maximum bending moment, you can see that it is 59 here. This 59 kilonewton meter is the maximum bending moment. So what you can directly write that. So maximum bending moment occurs at 59 or the 29 kilonewton meter. And of course, at that point, you know that it occurs at E. Maximum bending moment occurs at the point E. So if you write the expression for that maximum bending moment, so you'll be getting 29 kilonewton meter as the maximum bending moment here. But in this case, either it is 29 or 59, they are acting at the same point. Okay, so that is the maximum value of bending moment. So this is the complete problem of a simply supported beam. Here I have considered 3 types of loads: UDL, external couple, and concentrated load with overhang portion. So please understand this clearly. Today you solve this problem only, and the derivation what I explained, relationship between bending moment, shear force, and load intensity. You try to do that. It's a very simple derivation, very important derivation. And in this problem, first step is to find the reactions. To find the reactions RA and RB, we have to use the equilibrium conditions. Okay, by using equilibrium conditions, you can find the reactions. That is one thing. Then After that, first I have plotted shear force diagram. I explained you how to plot the shear force diagram. Start from the first point, move towards the last point. Upward forces, you move upwards. Downward forces, you come down. Okay, so that is the procedure. Above the horizontal line, positive shear force. Below the horizontal line, negative shear force. Then at some point, you may have shear force 0. So if you want to find the location of that point where the shear force is 0, so you transfer that point to this beam. Consider left side or right side, anything of that, and write down the shear force expression. Equate it to 0, you'll get the distance. So that is how we did this. Next, bending moment diagram. We calculated the bending moment at some points, important points at A, at C. At C, you have two values of bending moment because external couple is given. Left side and right side you have to calculate. Then at B, then at D. So at four points, 5 points you have calculated the bending moment, and that is plotted. When you are joining the points, UDL, if it is there, you have to join by a parabola. Here the load is UDL from A to B. So that's why you have two parabolas here. So this is from here to here parabola, from here to here parabola. Whereas here you have two values of moment because of that external couple. Okay. Then this is a straight line. So then after this, we have seen that bending moment is 0 at one point here, where it cuts that horizontal line, where the parabola cuts that horizontal line. There the bending moment is 0. So you have to find out the bending moment expression at that point and equate it to 0 to get the value of x2. So by considering left side of the section, we have done it. So that is how this problem has been done. So in the examination, so this will carry nearly 10 to 12 marks. So you should be minimum 10 marks will be there. If they ask you to draw bending moment diagram, shear force diagram, maximum bending moment value, and the location of where the shear force is 0, all those things if they ask, the 8 to 10 marks will be there for the problem. So you should do the same problem. Today you practice the same problem. Tomorrow I am going to explain 2 more problems of BMD and SFD. So you should be thorough with this because there will not be any choice in this. Choice will be there between BMD and SFD only. So only bending moment diagram, shear force diagram, relationship between bending moment, shear force, and load intensity. What is sagging bending moment? What is hogging bending moment? So only those questions will be there. And given the shear force diagram, sometimes they will ask you to find the bending moment diagram. So that type of problem also is there. I will take up that later. So today I explained the derivation of that relationship as well as one example of drawing BMD and SFD thoroughly. So same problem you just practice today and understand it clearly. So because coming problem in future problems I'll be explaining fast so that you understood. I think that you understood because first problem you try on your own whatever I have explained today. So same problem you take, analyze it. So try to draw the BMD and SFD for that problem. Understand the procedure because this online class, unless you work on paper, it is very difficult to understand. So how to find what is point of contraflexion or point of inflection means where the bending moment is 0. That point is called as point of contraflexion. They will ask you to locate that point. Locate the point means you have to find the distance of that point from one of the ends. So that is the meaning of location of that point. So these things I wanted to explain you today. So I will continue tomorrow. So write down the same problems and try to understand. So sign convention you should understand clearly. For bending moment, whether it is left side or right side of the section, upward forces give positive bending moment, downward forces give negative bending moment. Okay, that means upward forces give sagging bending moment, downward forces give negative bending moment. When you come to shear force, if you are taking left side of the section and calculating shear force, you have to take upward forces positive, downward forces negative. If you are taking right side of the section and if you are calculating shear force, downward is positive, upward is negative. So this is the sign convention I had explained. Be thorough. Only once you understand all these sign conventions, all the concepts, how to draw the shear force diagram I had explained, move up vertically, come down, all those things I have explained. So if you understand that, then only you can do any type of problem. You can easily score 10 out of 10 marks in this BMD and SFD, because a single problem can fetch you more marks here. Okay, so profiles you have to understand. BMD profile, if it is UDL, it is parabola. If it is triangular, it is cubic parabola. If it is a concentrated load, it is a straight line. Whereas shear force diagram, if it is concentrated load, it is constant. If it is UDL, it's a straight line. If it is UVL, it will be a parabola. So like 1 degree less. And also we have proved that rate of change of shear force is it gives the load intensity, that is dF by dx is minus W, and dm by dx is F. Okay, so that is the relationship between bending moment, shear force, and intensity of load. So these things we have covered today. So you have to practice. You just practice. Then if you have any doubts, then only you can ask. Unless you practice, it is very difficult to understand. I told you, I am keep on telling you. So practice the problems which have been covered in the class. Yes, 12 students. Today attendance is very poor. I don't know why. If you are absent, then you are the losers. A lot of syllabus is there. I cannot repeat the classes. It's very difficult. 1828 Tejas.
Present, sir.
30.
Yes, sir.
19002.
Yes, sir.
5. 005. Darshan. Darshan, there is problem always. I am going to put absent.
Present, sir.
ಏನಪ್ಪ ನಿಂದ ನೀನ್ ಯಾವಾಗಲೂ ಅಟೆಂಡೆನ್ಸ್ ಹೇಳೋದಿಲ್ಲ ಅಲ್ಲ, ಯಾಕೆ ಆನ್ ಮಾಡಿ ಹೊಟ್ಟೋಗ್ತೀಯ, ಏನ್ ಕತೆ?
ಇಲ್ಲ ಸರ್, ಇದ್ದೀನಿ.
ದಿವ್ಯಶ್ರೀ.
ಪ್ರೆಸೆಂಟ್ ಸರ್.
ಜ್ಯೋತಿ.
ಜಾನ್ವಿ.
ಜ್ಯೋತಿ ಅಲ್ಲ, ಜಾಹ್ನವಿ. ಜಾಹ್ನವಿ
ಪ್ರೆಸೆಂಟ್ ಸರ್.
007. 10 ಪದ್ಮ.
ಪ್ರೆಸೆಂಟ್ ಸರ್.
ಪ್ರೀತಿ 11.
ಪ್ರೆಸೆಂಟ್ ಸರ್.
Then 13 Medhesh.
Present, sir.
16 Sri Lakshmi.
Yes.
19
Sir.
Shweta.
ಪ್ರೆಸೆಂಟ್ ಸರ್.
Present, sir.
21 Surya.
Yes, sir.
1 2 3 4 5 6 7 8 9 10 11 12. Only 12 students. So practice the problems and the derivation which I have explained today. So then only you will understand. Otherwise, if you just keep it like aside, then even if I do 10 problems, you will never understand. So practice it, and it will be easy for you to do the next problems. So tomorrow we will continue. Okay.
Thank you, sir.